So now that we've spent some time thinking about what a differential equation is and even visualizing solutions to a differential equation using things like slope fields, let's start seeing if we can actually solve differential equations. And as we'll see, different types of differential equations might require different techniques, and some of them we might not be able to solve at all using analytic techniques. We'd have to resort to numeric techniques to estimate the solutions. But let's go to what I would argue is the simplest form of differential equation to solve, and that's what's called a separable differential equation. And we will see in a second why it is called a separable differential equation. So let's say that we have the derivative of y with respect to x is equal to negative x over y e to the x squared. So we have this differential equation, and we want to find the particular solution that goes through the point 0, 1. And I encourage you to pause this video, and I'll give you a hint. If you can, on one side of this equation, through algebra, separate out the y's and the dy's, and on the other side, have all of the x's and dx's, and then integrate, perhaps you can find the particular solution to this differential equation that contains this point. Now, if you can't do it, don't worry, because we're about to work through it. So as I said, let's use a little bit of algebra to get all the y's and dy's on one side and all the x's and dx's on the other side. So one way to, let's say I want to get all the y's and dy's on the left-hand side and all the x's and dx's on the right-hand side. Well, I can multiply both sides times y. So I can multiply both sides times y. That has the effect of putting the y's on the left-hand side. And then I can multiply both sides times dx. I can multiply both sides times dx. And we kind of you can treat these differentials as you would treat a variable when you're manipulating it to essentially separate out the variables. And so this will cancel with that. And so we are left with y dy is equal to negative x. And actually, let me write it this way. Let me write it as negative x e, actually I might want a little more space. So negative x e to the negative x squared dx. Now why is this interesting? Because we can integrate both sides. And now this also highlights why we call this separable. You won't be able to do this with every differential equation. You won't be able to algebraically separate the y's and dy's on one side and the x's and dx's on the other side. But this one we were able to. And so that's why this is called a separable differential equation. Differential equation. And it's usually the first technique that you should try. Hey, can I separate the y's and the x's? And as I said, this is not going to be true of many, if not most, differential equations. But now that we did this, we can integrate both sides. So let's do that. So I'll find a nice color to integrate with. So I'm going to integrate both sides. Now, if you integrate the left-hand side, what do you get? You get, and remember, we're integrating with respect to y here. So this is going to be y squared over 2. And we could put some constant there. I could call that plus c1. And if you're integrating now, that's going to be equal to, now the right-hand side, we're integrating with respect to x. And let's see, you could do u substitution, or you could recognize that, look, the derivative of negative x squared is going to be negative 2x. So if that was a 2 there, and if you don't want to change the value of the integral, you put the 1/2 right over there. And so now you could either do u substitution explicitly, or you could do it in your head, where you set u is equal to negative x squared, and then du will be negative 2x dx, or you can kind of do this in your head at this point. So I have something and its derivative, so I really could just integrate with respect to that something, with respect to that u. So this is going to be 1/2, this 1/2 right over here. The antiderivative of this is e to the negative x squared, and then of course I might have some other constant. I'll just call that c2. And once again, if this part over here, what I just did, seems strange, the u substitution, you might want to review that piece. Now, what can I do here? Well, I have a constant on the left-hand side. It's an arbitrary constant. We don't know what it is. I haven't used this initial condition yet, we could call it. So let me just subtract C1 from both sides. So if I just subtract C1 from both sides, I have an arbitrary, so this is going to cancel, and I have C2, so this is C1. So these are going to cancel, and C2 minus C1, these are both constants, arbitrary constants. We don't know what they are yet, and so we could just rewrite this as, on the left-hand side, we have y squared over 2 is equal to, on the right-hand side, I'll write 1/2 e, let me write that in blue just because I wrote it in blue before, 1/2 e to the negative x squared, and I'll just say C2 minus C1, let's just call that c. So if you take the sum of those two things, let's just call that c. And so now, this is kind of a general solution. We don't know what this constant is, and we haven't explicitly solved for y yet, but even in this form, we can now find a particular solution using this initial condition. And let me separate it out. This wasn't part of this original expression right over here, but using this initial condition. So it tells us when x is 0, y needs to be equal to 1. So we would have 1 squared, which is just 1, over 2, is equal to 1/2 e to the negative 0 squared. Well, that's just going to be, e to the 0 is just 1. So it's going to be 1/2 plus c. And just like that, we're able to figure out, if you subtract 1/2 from both sides, c is equal to 0. So the relationship between y and x that goes through this point, we could just set c is equal to 0. So that's equal to 0. That's 0 right over there. And so we are left with y squared over 2 is equal to e to the negative x squared over 2. Now we can multiply both sides by 2, and we're going to get y squared, let me do that. So we're going to get y squared is equal to e to the negative x squared. Now, we can take the square root of both sides, and you could say, well, look, y squared is equal to this, so y could be equal to the plus or minus square root of e to the negative x squared, But they gave us an initial condition where y is actually positive. So we're finding the particular solution that goes through this point. That means y is going to be the positive square root. If this was the point 0, negative 1, then we would say y is the negative square root. But we know that y is the positive square root. It's the principal root right over there. Actually, let me do that a little bit neater. So we can get rid of, whoops, I thought I was writing in black. So we can get rid of this right over here. We're only going to be dealing with the positive square root. Or we could write y is equal to e to the negative x squared to the 1/2 power, and that of course is equal to e to the negative x squared over 2. So this right over here is, or y equals e to the negative x squared over 2 is a particular solution that satisfies the initial conditions to this original differential equation. So just like that, because we were able to, just as a review, because this differential equation was set up in a way, or because we could algebraically separate the y's dy's from the x's dx's, we're able to just separate them out algebraically, integrate both sides, and use the information given in the initial condition to find the particular solution.